Hello everyone, I'm Lou Del Monte and welcome to Del Monte on Science. We're going to pick up where we left off last time. We were discussing the early inflation of the universe in our last video post. Now we're going to use the Big Bang duality theory to explain another mystery, and that is, why is there only matter and photons in the universe? We see very little antimatter. In theory, we should see as much antimatter as we do matter in the initial Big Bang. But we're going to look at the equation, and we're going to look at data that comes out of about 8 years of particle accelerator experiments. And this, I think, will give us a huge insight into why the universe is composed mainly of matter and photons. Okay, so let's take a look at that. Last time we talked about, in the Big Bang duality theory, that there's a superuniverse. It gives rise to infinitely energy dense particle pair. These are virtual particles, and the matter and antimatter collide. That causes the initial Big Bang. From that you get a violent reaction using this equation right here. A lot of energy is given off in electromagnetic radiation. That causes the initial inflation of the universe. And now, though, if you look at this equation, you would think, well, I should have some antimatter. And we're going to talk about that right now. The way I look at this equation is from the standpoint of a chemist. And I look at it as a phenomenological equation. In other words, what actually happens when we collide matter and antimatter in a particle accelerator? What they found out over the last 8 years, this is a surprising discovery, is that when antimatter 1 collides with matter 1, you get matter 2 and antimatter 2 and some photons. But when you compare matter 2, it's greater than the antimatter by about 1%. 1%. In other words, you're getting slightly more matter in this reaction, just slightly more than you are getting antimatter, 1%. What does that mean? Doesn't seem like a lot, right? But what it means is that as the collision, if I consider this a very intimate collision, in other words, every element of the particle is connecting with every other element of the antimatter particle, then what actually happens is this goes to completion. I essentially use up all the antimatter, and I get M2 plus electromagnetic radiation, photons. And that, if we look at that, that's the universe we have today. Now, I know there's been a lot of question about, well, why don't we see any antimatter in the universe? The answer is that when we actually do the experiments in a particle collider, we notice that it favors matter, okay? And that's not well understood. Now, there are what they call barogenesis theories, barogenesis theories, I might have mispronounced that. And basically what they do is they assume an asymmetry of physical laws. I don't do that, okay? I look at this as a chemical reaction and I say it's phenomenological. It is the way it is because it is the way it is. If you're going to assume an asymmetry in physical laws, you're on pretty shaky ground. The best theory in science, which is the special theory of relativity, it's withstood over 100 years of probing, testing, and it's been considered the golden standard of scientific theories. One of the pillars of that theory is that the laws of physics are the same in all inertial frames of reference. And so as soon as you start saying I have an asymmetry in physical laws, that means that if I do the experiment today, under the identical conditions tomorrow, it'll be different. If I do it in one corner of the room under the identical conditions, it'll be different. So asymmetry in physical laws is pretty speculative. And as I said, they call that barogenesis type theories. And I'm not a big fan of that. But I am a fan of looking at what the experimental data says. And what it does say, it does favor matter. And it's very slight, but when this goes to completion, you will end up with exactly the universe we have, which is matter and electromagnetic radiation, photons, and very little antimatter. We see very little antimatter in the universe. And that is, again, from the Big Bang duality theory, starting with the matter and antimatter particles, the infinitely energy-dense particles. That explains why we're missing antimatter. Thank you very much.